Assalamualaikum warahmatullahi wabarakatuh. Today, me and my teammate are gonna present an article that been assigned to us, which is analysis of vegetables oils using gas chromatography. This presentation is for subject CHM261, which is spectroscopic and chromatographic analysis, and we are from class AS1254A.
So, before we start, I would like to introduce myself. My name is Muhammad Ainul Hakimi bin Sofiani, and I would like to talk about the introduction. First of all, gas chromatography is a fundamental technique that is widely used in analytical chemistry for separating and analyzing compounds that can be vaporized without decomposition. Among the various instruments developed for this purpose, the Shimadzu GC2010 Pro gas chromatograph stands out due to its high performance, reliability, and precision. In this experiment, the Shimadzu GC2010 Pro was paired with the AOC20i auto injector. This system will enable efficient sample introduction and automation, making it ideal for high throughput environment.
Next, we will move to the problem statement and why this experiment is conducted. Vegetable oils are made up of complex triglycerides, and many of them look very similar chemically. This makes it hard to identify and differentiate them accurately. Traditionally, we need to do a process called derivation before analysis, which takes extra time and effort. This can be inefficient, especially in industrial or commercial settings. Because of that, there is a need for a faster and more reliable method that can analyze oils without complicated preparation. So, in this study, we focus on using gas chromatography or GC as a direct method to identify and compare different vegetable oils based on their unique chromatographic pattern.
Next, the objective. First, to determine the retention time of a selected vegetable oils through gas chromatography. Second, to identify the triglyceride peaks in a selected vegetable oils. Third, to generate chromatograms for each oil type and compare their profiles. Next, I will explain the methodology. First, sample injection. A small amount of oil sample is injected into the system using syringe. Second, carrier gas flow. An inert gas like helium or nitrogen pushes the sample through the system, and the sample will enter a long thin column coated with special material. For example, in this experiment, RTX 65TG was used as a column. 4. Separation process. The sample will separate based on how strongly they interact with the column material and their boiling points. Each compound will exit the column at different time, which is their retention time. 5. Detector. The detector used in this experiment is FID, which is flame ionization detector. The FID will burn the compound and measures ion produced, giving a signal proportional to the amount present. Lastly, data processing unit. The detector will send signal to the computer and it will plot a chromatogram, which is a graph of peaks.
Now we're gonna move to findings. In this experiment, we use gas chromatography to study the triglyceride content in 4 types of vegetable oils, which is canola oil, soybean oil, olive oil, and sunflower oil. The oils were injected into the GC system without derivatization. the column and detector were both held at high temperatures, which is around 365 Celsius, as shown in table 1. Because triglycerides have high boiling points and need more heat to vaporize. After the oils pass through the GC column, we got chromatograms, which are graphs showing peaks at different retention times. Each peak represents a different triglyceride or group of similar compounds. Here's what we found. In canola oil, in figure 2, we found that canola oil had fewer peaks, but some of them were very tall. This suggests that canola oil contains a small number of major triglycerides, which are present in higher amounts. Next, we got soybean oil in figure 3, which had more peak spread across the whole retention time range. This tells us that soybean oil has more types of triglyceride and it's more chemically complex. In olive oil, we had 2 dominant peaks and a few smaller ones. This pattern shows that olive oil contains mostly 1 or 2 main triglycerides, which is typical because olive oil is rich in oleic acid. And the last one is sunflower oil in figure 5. Sunflower oil gave us a very complex chromatogram. It had many peaks, as you can see there. That many peaks come with very different sizes. This indicates a wide range of triglycerides, probably due to its high linoleic acid content and variation in fatty acid chains. In figure 6, we used peak areas to see the relative amount of each component. Larger peak areas mean higher concentration of those triglycerides. So the larger the area, the higher the concentration of triglyceride. This helps us to understand the composition of the oils more precisely.
Last but not least, in figure 7, we compare all the chromatograms in a single graph. This makes it easier to visually observe how the oils actually differ. The unique patterns of each oil confirm that their chemical compositions are distinct.
Moving to the conclusion, to conclude this analysis, I want to highlight a few key points based on the chromatographic data that we obtained or we used. To begin with, we saw that each type of oil produced a unique chromatogram. The number of peaks, their height, their retention times were different from canola, soybean, olive, and sunflower oil. This shows that each oil has its own triglyceride composition. Second, the differences in the peak patterns help us compare and even identify oils. For example, the tall, simple peak in olive oil are very different from the more complex pattern we saw in sunflower or soybean oil. Third, these experiments show that gas chromatography is a powerful tool for oil analysis. Even without any chemical modification or derivatization, we were still able to get meaningful data, as long as we used a high enough temperature to vaporize the triglyceride. So in real-world application, this technique can be used for quality control, purity testing, and adulteration detection. We can check that oils meet certain standards through quality control, and then we can also confirm if the oil is pure or mixed with something else through purity testing. And the last one, we can find out if the factory put a cheap oil or add the cheap oil into an expensive one through adulteration detection. Thank you so much.